To create a physical heart model that can faithfully represent both the dynamic cardiac motion and the internal cardiac anatomy, we took a biohybrid approach where we use soft robotic techniques to replicate physiological cardiac motion and directly utilize biological structures to represent the detailed anatomy. That way, the active soft robotic myocardium drives the motion of the passive inner heart tissue with preserved anatomical details. In our approach to mimicking the cardiac motion, we programmed the soft robotic myocardium by replicating the fiber orientations with linearly contracting actuators. We dissected the ventricular muscle to a singular muscular band that has rather simple fiber orientations. We created a soft robotic equivalent of the unraveled heart tissue structure by orienting soft artificial muscles along the major fiber orientations. Then the soft robotic band was rewrapped around the inner heart tissue back to the three-dimensional arrangement to create the global fiber architecture as well as the cardiac motion of the heart. First, we developed a process for making the biohybrid heart from an explanted porcine heart that is chemically preserved. We create an outer mold by casting the heart's outer ventricular wall geometry. Then we perform the dissection onto the heart in a layer-wise manner, following the cardiomyocyte orientation to carefully remove the ventricular muscle tissues, including the left ventricular and septal portion. So the resulting endocardial scaffold is essentially the whole heart minus the ventricular muscles, leaving all the intracardiac structures intact. Then we position this tissue into the outer mold and pour silicone elastomer to cast the synthetic myocardium. We use a custom-made soft adhesive to assemble the synthetic myocardium with the endocardial scaffold to make the biohybrid heart. To program the cardiac motion in the soft matrix portion, we first scan the muscle fiber orientations of the unraveled heart tissue and identify the major fiber tracts. Then we designed 2D robotic band by orienting flat-plated pneumatic artificial muscles along the fiber orientations of the organic tissue band. This clip shows cyclic motion of the soft robotic band as the actuators contract. Now that we have the soft robotic band built, we need to assemble it back to the inner heart tissue. We first apply tissue seal adhesive, which is a custom-made soft adhesive to bond the organic tissue with silicone elastomer. Then, before the adhesive cures, we rewrap the soft robotic band around the left ventricular inner heart tissue to form the three-dimensional structure of the ventricular muscles, as shown in this video. Then the assembly is positioned onto the outer mold and additional soft matrix is poured on to secure the assembly and reconstruct the outer ventricular wall geometry. The resulting piece is a three-dimensional biorobotic hybrid heart, combining the active soft robotic myocardium with preserved inner heart tissue structures. The soft robotic matrix contains multiple soft contracting actuators which are connected to the air source that gives controlled input to generate desired cyclic actuation patterns. The endocardial portion of the organic tissue is hidden by the soft robotic matrix in this picture, but you can see the other parts of the heart tissue like the vessels and the atria. And when we actuate the heart cyclically, this is what it looks like from the outside. And using the 4D MRI, you can visualize the motion of each of the structures a little better. You're looking at the short axis view of the biorobotic hybrid heart. The soft synthetic matrix, which is gray in color here, is surrounding the endocardial tissues, which is bright in color. Then when we actuate the heart, you can see the actuator cavities are opening up and displace the endocardial tissues inwards, reducing the size of the left ventricular chamber. We also observe the motion of the bio-robotic hybrid heart under echocardiography. You're looking at the long axis view of the heart. And as you can see, there is significant amount of volume reduction in the left ventricle, around 70%, comparable to a healthy heart, driven by the soft robotic actuation. As a part of the next step, we are also developing an in silico model for the soft robotic myocardium in our efforts to optimize the design for hemodynamic performance and motion. We are testing multiple designs of the soft robotic myocardium for optimal performance. In this model, we simulate the motion and evaluate the pressure-volume relationships in a dynamic virtual lump parameter model to evaluate each design. In this short clip, you can observe predicted motion of one particular design of the soft robotic matrix containing an array of multiple contracting actuators. In the near future, we hope to connect the optimized birobotic hybrid heart in a physical mock circulatory loop to make a realistic cardiovascular benchtop model where the heart would autonomously drive the blood flow. Thank you for your attention, and if you have any questions, please feel free to chat with me in the box below.